So pictured here is an oxygen extremity chamber, and here is of a hyperbaric oxygen chamber, and I will say more about that in a bit. So now as a warning, so I've given enough talks in front of math groups, and granted this isn't the most mathematical group, but I've given enough talks in front of math groups that I've actually developed a warning slide for grotesque pictures. So now you've been fairly warned about grotesque pictures, and so with that said, here's the next slide. And so, okay. So anyhow, yeah, so just a little bit about myself. I received my PhD from North Carolina State University in 2005. My dissertation work, this isn't the actual title, but was on mathematics of cartilage mechanics. I worked on 3 different problems at that time. From there, I went on to do a postdoc. I was there for 3 years at the Mathematical Bioscience Institute. While I was there, I got to meet Judy Day, for example. I worked on problems involving wound healing, lupus, and hemodialysis. From there, I got a position at Western Kentucky University, and I've continued working on wound healing problems. Now, some of my current interests while I'm here is to identify ways to try to connect mathematics better to therapies. That's one of the reasons why I chose to get into optimal control theory a couple years ago. I'm interested in connecting mathematical models to data. We just had a paper that's going to come out any day now in the Bulletin of Mathematical Biology that does a little bit of that. I'm interested in potentially expanding my mathematical and biological interests. So could be numerical methods, could be inflammation. I don't know. But I'm always interested, or I have some interest at least in terms of trying to expand my interests, and then also incorporating data into a mathematical classroom. And that I teach a lot of classes in calculus, differential equations, modeling, numerical analysis, things like that. And so how can we better incorporate and develop applied type problems and things like that that could be useful and better serve the students for those classes. And so now on the next slide, I've got a picture of a diabetic foot ulcer. So if you don't like those, then yeah, go ahead. So, okay. Yeah, so I'm also an editor of the SMB Digest, which is a weekly email that basically we mostly send out email advertisements, advertises things like workshops, jobs, those are the primary things that are advertised there, but couldn't be other things. And so I'm yeah. And so I actually send out the emails during the summer months, and so usually from about the middle of May to about the middle of September, I do that. So anything else that I need to include? Anybody? So.
Somebody else sent them out the other month,
Right. But once in a while, if there's issues to discuss, those of us that are editors, we'll discuss it. And Wandy's, some of you know Wandy Ding. She's an editor as well, and so. All right, so here's my lovely picture of a diabetic foot ulcer, and so this is kind of the worst picture that I have in the entire talk. And so, anyhow, the wounds I tend to work with are chronic wounds. The way that we typically define a chronic wound is in terms of time of healing. Typical wound would heal in about 2 to 4 weeks. However, these chronic wounds are often the consequence of a more serious problem like diabetes and heart disease. And so the picture on the left is of a diabetic foot ulcer. With proper treatment, we can heal this, like in the picture on the right. But left untreated, we can have a problem with infection, amputation, or even death. Furthermore, the cost of treatment is on the order of $5 to $10 billion per year. And I've even seen one recent estimate to say that it could be as much as $25 billion per year in the U.S. And so,
just for diabetic?
Chronic wounds, more generally for chronic wounds, I should say, yeah. And so, but that's just in the U.S. These different estimates. And so, I think I saw a recent estimate in the U.K. that's £1 billion per year or something like that there. So, clearly there's a need to try to improve these types of wounds. Also, if you guys have questions as we go along, I don't mind trying to answer questions as we go along. And so, that's the end of the grotesque pictures. Well, anyhow, so okay, so presented here is a layer of skin. Notice on the epidermal layer there are no blood vessels, but in the dermal layer there are lots of blood vessels. So in a deep skin wound, the blood vessels gets cut. This is a problem because the blood helps move junk and debris within the wound environment, while also providing a way of providing nutrients and in particular oxygen to the wound region. Why is oxygen important? Well, oxygen cells need oxygen in order to function properly within the wound environment. Inflammatory cells use the oxygen to help fight off infection. Fibroblasts use the extra oxygen, use as much oxygen as possible to help produce extracellular matrix, etc. Some things that we know about oxygen and wound healing is that if we increase the level of oxygen, we promote a healing response, but if we have too much oxygen, this can derail tissue repair, and at the same time, if we have too little oxygen, vessel growth is stunted. And so the question becomes, what is the right amount of oxygen, and can we control the healing response based on the amount of oxygen that we give? Or at least that's one of the questions I've been working on various problems like this over the last few years. Some ways of administering oxygen therapy are topical oxygen therapy and hyperbaric oxygen therapy. And so in topical oxygen therapy, one way of administering it is using what's called an oxygen extremity machine, oxygen extremity chamber. And so pure oxygen is delivered to a wound like this, such that very little can actually escape the chamber. And typical treatment is on the order of about 90 minutes per day for a period of a few days, followed by a cycle of rest. And then this process is repeated until the wound has ideally healed. For hyperbaric oxygen therapy, pure oxygen is breathed in. The increased pressure actually helps dissolve oxygen, which actually then helps deliver more oxygen to the wound region. Typical treatment is on the order of once or twice per day at 2 to 3 times the normal pressure for a period of about 2 to 6 weeks. Some issues with hyperbaric oxygen, though, is that it can be quite costly. So only the most severe of wounds typically you would use hyperbaric oxygen for. There's a risk of oxygen toxicity. However, there are a number of ways that some of that's minimized, minimizing the pressure, minimized duration of treatment. And also one of the things that they'll sometimes do, they won't always tell the patients that they're doing this, is that in the middle of therapy, they'll actually give you like a 5-minute break from, as opposed to breathing in pure oxygen, you're breathing in a normal level of oxygen. And so it's just some little things that they've done to actually minimize the risk. And they've done this long enough that the risk is fairly minimal at this point, but there's still a risk there. And then also optimal treatment strategies are not necessarily known. That just because a treatment is standardized doesn't necessarily mean it's optimal. And so this is kind of the motivation behind some of the optimal control of what I'm going to talk about, optimal control using oxygen therapy. And so if we're going to model the wound healing process, we need to know a little bit about the wound healing process. And so the wound healing process is usually described in terms of either 3 or 4 temporal yet overlapping phases. One phase is an inflammatory phase. In that phase, platelets and proteins from broken blood vessels will help form a clot. Inflammatory cells such as neutrophils and macrophages will migrate into the wound region to degrade necrotic tissue, remove bacteria, etc. This is typically on the order of days. Sometimes you'll see it as 3 phases. Sometimes you'll see it as 4 phases. If you see it as 4, then these 2 processes are usually split into 2 separate phases. And so the next phase is a proliferative phase. In this phase, fibroblasts will migrate into and produce extracellular matrix. This tends to be the scar tissue, or can be the scar tissue that forms within the wound region. Endothelial cells, what they'll do is they will migrate into the wound region and start to line up and form tiny lumen. And then when blood starts to flow through, you'll have capillaries, new capillaries that are formed within the wound region. This process is called angiogenesis, the formation of blood vessels from existing vasculature. This typically lasts on the order of weeks. And the last phase is the remodeling phase. In the remodeling phase, the fibroblasts produce new extracellular matrix, degrade extracellular matrix, and reorganize some of the existing extracellular matrix. This is done to try to enhance the mechanical strength of the scar tissue, but even after remodeling, the new tissue is not as good as the original. And so this is typically on the order of months. So one of the things I tried to do a couple of years ago was actually try to put together a model with capturing some of this stuff. And in doing so, I only formulated a model with 14 equations. Probably not the best approach to just work with 14 equations, but it is handy sometimes to have this and to go back and refer to this. And so what I did was I took these 14 equations, and actually, there's a network diagram of, or attempted a network diagram of those equations, and I subdivided this into more of an inflammatory response to the presence of bacteria, and then more of a reparative response. And so I actually subdivided this, and actually, have since then been working on kind of 2 different problems. And so this is actually kind of the motivation behind, some of the steps that I've taken to kind of get to this point, so to speak. So I'm going to talk a little bit now about bacterial inflammation, or our minimal model that we have for that. Main cell types for the inflammatory response are neutrophils and macrophages. The neutrophils typically peak at 1 to 2 days. Monocytes come in, become activated macrophages. They typically peak at 2 to 4 days, and they initiate the reparative response. So if we're thinking about bacterial inflammation, usually when this happens, there's a prolonged inflammation whereby inflammatory cells will in short recruit more inflammatory cells, produce a number of degrading enzymes, and this leads to poor healing, excess scar formation. One cause for that can be a lack of oxygen in the wound, or at least some people have argued that. Neutrophils need adequate oxygen to help fight bacterial infection, and the ability to kill bacteria can delay the healing process and increase tissue damage. I've also gotten into trying to model oxidative killing of bacteria, and so with this, talking just a little bit about reactive oxygen species. Almost every cell converts oxygen to ROS. In high levels, it can be damaging to the wound, but in low levels, it's believed to actually mediate some of the cellular responses. And note that in chronic wounds, the enzyme that's used to produce ROS is inhibited. And so we formed a simplified model here. So I've actually reduced this down to 6 variables, and I actually go from 6 down to 3. So this is one way that sometimes a modeler thinks about this in a simpler way, so to speak, but still tries to capture some of the dynamics of this. And so I started by reducing the number of inflammatory cells down from 2 to 1. You'll see models. Some models actually have both macrophages and neutrophils, while others will just call them one cell type. And so the neutrophils from here on out are more generally inflammatory cells. So neutrophils are the primary ones in this model. We needed a way to initiate the process, so I just simply said let's assume the platelets decay as a way of just initiating more of an inflammatory response to recruit the neutrophils in this, so to speak. So the neutrophils, we have initial recruitment, enhanced recruitment due to the detection of the presence of bacteria. It's oxygen dependent, and then death is also dependent upon bacteria being present in the wound as well. Oxygen, it diffuses in, so at least in an ODE sense, it's diffusing in from the wound edge, and there's uptake by neutrophils by some of the bacteria, as well as a little bit of decay. For the we have we have an equation for the ROS that's produced by the neutrophils, as well as some of the other cells there. And then there's loss when there's uptake by bacteria and general decay. The assumption that we made in the model here is that we make what's called a quasi-steady state assumption, and when the rate of change of one variable is fast, in comparison to a lot of the others in the model, we assume that we can make an assumption that that derivative is 0 for all time. And so when you do that, that actually reduces the number of equations, because you can actually take that and actually solve that for one of the variables in the model. And then finally, we have a term for the bacteria, where we have proliferation, oxidative killing, and then general death, so to speak. And so we've actually reduced this down to 3-variable ODE model. I've also got a corresponding PDE model that I will present very briefly in a bit. And so I've actually, on top of that, reduced this down from 3 variables down to 2 variables by assuming that some of the oxygen, assuming that some of the parameters become oxygen dependent. And so what we did was we conducted, so not getting too much into the details, but just a little bit. I had some students conduct what's called a steady state analysis. Reason why this can be important is that we're looking at what happens at the end time of the model. However you define the end time here, would probably be days or weeks. And in the end time, what you want to do is make sure that you can get literally different states. In this case, like a healing state or non-healing state, or in this case, healing would be removal of bacteria. Non-healing would be that the bacteria persists. And so quick idea of doing that analysis would be to set the derivatives equal to 0. We find the null Klein equations by actually, after setting the derivatives equal to 0, solving both of them for n in terms of b, and then looking for points of intersection. And when we do that, we identify some of the different steady states and identify conditions for existence and stability. So I had another student actually identify stable manifold with regard to these two equations. And basically what this is saying here is that if I have an initial condition for the neutrophils and bacteria to start in this region, so a high level of neutrophils, low level of bacteria, I'm going to get a healing response, meaning that the bacteria is going away. And if I start over here, the bacteria is going to persist. And so that's just a little bit of analysis for this minimal model of interactions of inflammatory cells and bacteria with oxidative killing. What I'm interested in doing is taking this model and then extensions of this model as well, and trying to look at treatment strategies using optimal control theory. Optimal control theory has never really been applied to wound healing models before. However, it has been employed, to study, a number of other problems, including cancer and HIV. So the idea of optimal control, or a way of thinking about this, is that there's at least one or more extra variables that you have in the problem that you can control in some way. In our case, it would be oxygen therapy. And with regard to optimal control theory, what we're trying to do is find an optimal solution, so to speak, to this problem. And so what I'm doing here is actually trying to literally minimize the amount of bacteria combined with, so on this slide, G ends up representing the supplemental oxygen. On most of the other slides, U represents the supplemental oxygen. And so we've considered some different cases. In this particular case, I've just got a case, what happens if you have a nonlinear response versus a linear response. And one of the things that can be interesting about this is that sometimes the linear response can be a harder problem than the nonlinear problem. One of the reasons being is that you could think of it as trying to minimize a line segment. And if you do that, the minimum is either going to be at one end or at the other, and you could get a switch from one state to another. And so one of the issues that you have with that then is that you can get a discontinuous control, which can be a little more challenging to deal with. There's also issues with singular controls and such like that too. We've employed Pontryagin maximum, or more specifically minimum principle to this. What we're basically doing is we actually append the ODEs to our objective functional. This is a lot like Lagrange multipliers and multivariable calculus. And so what we get here then is, we formulate a Hamiltonian which combines the two, and we have these additional adjoint variables. And so what this ends up doing, in short, is that it provides a set of necessary conditions that we need to satisfy in order to possibly have an optimal solution to this. And so what we end up doing then is that we solve our state equations. We have to solve both our state equations. So this dx dt represents our differential equations for the bacteria, neutrophils, and oxygen. We have to solve those. In this particular problem, they each have initial conditions. And then on top of that, out of this, we get a set of necessary conditions that basically allow us to say that we have a second set of differential equations that we have to solve, these adjoint equations, and we have to solve combined with a terminal condition, so to speak. We solve them using, we initially solved them using the forward-backward sweep that's outlined in Suzanne's book. We made some modifications to that using the steepest descent algorithm. And our initial set of results for this would actually look something like this, whereby this right here is actually the control. And so what this is saying is this is our initial control variable, and if we do this, then the bacterial level for this set of parameter values actually goes to 0. What we wanted to do is, we've done some work since then to actually try to get a better set of, or more biologically meaningful set of results. And so a more recent version of something like this looks something like this. And what we have here is that I'm actually administering oxygen therapy for 90 minutes per day. This is having an effect in terms of the bacterial levels here, but it's not quite getting the bacterial levels to 0. So what I have here, and one of the things to note here is that on this graph, time is in days. On this graph, time, and I should have written this in, is in weeks. Well, so getting back to here, the bacterial level's not quite going, not quite going away. So what we decided to do is then at the 5-week point to increase the amount of time of therapy from what would be 90 minutes to 105 minutes. And with that, we get the bacterial levels to actually go to zero. And so this is better capturing the dynamics than our original simulation has on that. Yeah.
So,
Go ahead.
in terms of the neutrophils, their half-life is about 6 hours, 24 hours. So neutrophils are dying off. I mean, would you also expect to see, a tighter oscillation of their populations as well?
Right. Well, this is also average. This could become average population of the neutrophils combined with macrophages. Although the neutrophils come in and macrophages will yes,
the neutrophils, right? So
yeah. There's
I don't know. I was just looking at it thinking we would see more variation in the neutrophil population, especially since I think I understood in the beginning that
Mhm.
oxygen repressed their ability to enter, right? Oxygen level.
right. Yeah, right. And we have this as a function of the oxygen levels, and so, but, but, and so. So, other questions? So, and as I said, what I'm mostly trying to do here is just present an overview of kind of everything I'm working on. So I'm trying not to get into too many details, but present a variety of problems so that we can get into the details either now or later, or so to speak. And so this is our ODE model on this, and so I've also got a corresponding PDE model with neutrophils. We've added an extra variable, a chemo attractant or chemotactic response to this, where we assume that it diffuses in, that this is actually produced by bacteria, and then there's some decay. One of the differences between the ODEs and PDE models, ODE models, roughly speaking, give us average concentrations over time. PDEs allow us to have both spatial and temporal variations, and in some ways, one can make an argument that both are important in the sense that a lot of the data that we might be working with is time varying or is average to begin with, but yet the tissue itself is highly heterogeneous. So I actually like having both in that sense. Oxygen equation looks similar, but with diffusion, and bacteria equation at least is initially similar. This was initial set of simulations on this. There's a lot more work that needs to be done. This is actually without a chemoattractant, and one of the issues that we had with this, is that the chemoattractant, the neutrophils, the inflammatory cells, migration of the inflammatory cells is highly dependent upon a gradient of oxygen. At least that's what we initially tried, and we weren't getting reasonable gradients of that. So that's why we actually incorporated a chemoattractant to actually get a better gradient, better movement in than what I initially have here. I had some students actually do a little bit of analysis for an honors project on this. And then I had a student that was interested in functional analysis. So what we did was we actually formulated, do a preliminary formulation of an optimal control problem, and to start looking at some functional analysis behind it. I'm not going to really get into a lot of the functional analysis, but just I'm just kind of mentioning this up here, where we actually this would in brief is the weak formulation for this. And the student got into doing some work in terms of proving existence and uniqueness, and so the initial work was to try to follow the work of Yagi et al. That actually dealt with trying to prove existence for the Keller-Siegel equations, and our equations are similar in form but have a different set of boundary conditions, and so that's something that we actually have to deal with going forward. And so with the PD optimal control, we're interested in existence of solutions as well as numerical solutions of this. And so future work on this problem is I definitely want to consider a larger model. I mean, right now I'm just defining healing as the bacterial level is going to zero, but there's a lot more that's going on here. And then, like, even if the bacterial level goes to zero, we want to see more of to look at what happens after that as well. And so, so I want to consider a larger model. But when I initially got into the optimal control formulation, I wanted to start with a reduced model, so to speak. I wanted a PDE model will allow us to better distinguish between the different therapies. Allow us, for more spatial variation, which makes it easier to distinguish the different therapies. With the ODE model, we can do some distinguishing between maximum amounts of oxygen and things like that, but we're limited in that sense. We want to eventually consider a more mechanical model. Think of it, trying to incorporate a biofilm. We eventually would like to connect this with data, or as we get more biological results, then some of my collaborators or some of the people I've worked with in the past at Ohio State said they would try to run some experiments if we can get grant money to do that. And then other things that we could consider would be to look at multiple controls. There was a study out there that showed that there's a possible synergistic effect of combining hyperbaric oxygen with topical application of growth factors. And so, questions on this part of it? Yeah.
When you speak about biofilm, so there's models out there trying to model
Yeah.
biofilm.
Right. And so we'd probably incorporate that work into this as well.
A model versus a model, a model inside a model.
Well, I mean, I would, even some of these equations, I took elements of other models, to incorporate some of that into that as well. And so yeah, I mean, there's models that have. As I said, one of the things that I haven't seen a lot of is the oxidative response in some of the models. So that's one of the things I think is novel about this minimal model in comparison to some of the other wound healing models out there. So other questions on this, and so.
I'm just wondering about how you're going to tie it to the data, because experimentally, what will your colleagues be measuring in the animal model? So a lot of times
Yeah.
they'll take LPS or bacteria, and they'll
Right. So what?
stick it into the
Go ahead.
back thigh,
Mm-hmm.
and then how you
Right. So they'll make a wound on a pig. Pigs tend to correspond better to human healing responses than say mice. The reason being is that with mice, the bulk of wound closure tends to be more of a contractive response, whereas with humans it tends not to be that way. It's only the wound closure for, I think, mice is something like 80% wound contracture, whereas with humans it's something like 30% at most. So
So will they measure, like on the neutrophil component, will they bother with that?
yes, yeah. So the thing that I really want them to measure would be not only bacterial loads, and how that change, at least how that changes over time, but then also neutrophil levels, and then also perhaps some of the other cell types that are not included in the model but could be included in a larger model, like fibroblast levels and such.
About whether or not the neutrophil is activated or not? Or are you just looking for presence and absence of neutrophils?
Right now it's presence. Right now this would be presence and absence, but then we could incorporate. Yeah, there is a model out there that gets into inactive and active forms as well. So there are ways of being able to deal with that too. But there are very few models that actually have time data of cell count, so to speak. More from what I've seen on the wound healing side, I've mostly seen more like measurements of protein levels and then wound closure. Yeah.
Which would be an enzymatic activity.
Right. And that's actually the second half of my talk. But yeah. The other problem that I've worked on is actually trying to combine data and wound healing. So some of you heard this a few weeks ago at the casual seminar. So in that regard, some of you have seen it. I'm going to keep this a little bit more brief. One of the things that actually got me in, or one of the things that one of the first places that I actually got working with data was when I was at the Mathematical Bioscience Institute. Or I did a little bit of work with data when I was a grad student, but that was mostly just curve fitting, and that was about the extent of it. And so kind of my first opportunity to work with data was we were working with some nephrologists. They were interested in a problem in lupus, and they gave us a spreadsheet that looks something like this. And here's this. Can you do some mathematics with this, so to speak? And And so what we did is we went back to the nephrologist and said, well, we're not sure exactly what to do with this, but what could be helpful would be to pick out the variables that you think might most contribute to a lupus flare. And so what they did was they actually gave us some data that looks something like this, that they picked out in particular 4 representative patients and some of the corresponding data with that. And what we ended up doing was we formulated a mathematical model with this, and we actually curve fit it up to a point of when a lupus flare, when they started actually treating a lupus flare, so to speak. And so this was actually my first introduction this was really in some sense my first introduction in terms of trying to work with data. And so got different colors here, but anyhow. And so with regard to trying to do this for wound healing, I actually formulated a mathematical model trying to formulate a mathematical model that corresponds to MMP and TIMP data in a wound. And so MMPs, what they do is that they degrade all the components of the ECM. They're essential for every phase of the wound healing process. For example, they help destroy the provisional extracellular matrix. This helps cells migrate into the wound region. And note that actually a successful healing response can be dependent upon both spatial and temporal patterns of expression. So we could even at some point consider a PDE model of this as well, perhaps. MMPs are different isoforms of MMPs. They can act on collagens, gelatins, etc. There's also tissue inhibitors of MMPs, and so what the tissue inhibitors do is that they will actually bind to the MMPs, inactivating them. When they form a complex, there tends to be 4 subgroups, 4 isoforms of the tissue inhibitors. The one that was most significant to us was TIMP1, because it's more likely to bind to MMP1 and TIMP1. And when there's an inflammatory phase, when the inflammatory phase is exaggerated, there can be excess levels of MMPs, TIMP levels can be reduced, the ECM can be broken down, etc. And so this actually started as an RAU project, where we initially just initially formulated a mathematical model similar to the one that I presented earlier, although it was more, different context, more of a reparative response model, so to speak. And during the summer, we actually came across this paper. And so at the end of the summer, what I actually decided to do was, as a student project, see if we could actually formulate a mathematical model that actually corresponds to some of the data that's in this paper, and that also perhaps even corresponds to one of the conclusions in the paper, which is the ratio of MMP1 to TIMP1 acts as a predictor of a successful healing response. And so that's actually how I got into this problem in the first place. And so the data itself actually measures levels of the different isoforms of MMPs and TIMPs in patients with type 2 diabetes. These are patients that have a chronic wound using this particular definition for a chronic wound. In this particular case, they didn't want any infection in the wound because that can actually increase the level of MMPs in the wound. And so data was collected at 0, 1, 2, 4, 8, and 12 weeks. And the way that they actually collected the data was actually put a strip next to a chronic wound, next to, say, a diabetic foot ulcer. And they actually collected wound fluid for 5 minutes. And they counted levels of MMPs and TIMPs. And then they also measured the wound size. And so our data, I think so the next slide, the data looks something like this. The patients were subdivided into what they called good healers and bad healers, dependent upon the actual healing response. And so what I have here are MMP and TIMP levels for good healers versus that for bad healers. And then this is also the percentage of wound closure. And note that this is actually average data. And so that was all we had at the time. We more recently got the individual patient data, which is kind of one of the steps or one of the things that we want to do going forward on this, to work with the individual patient data. So with that, we formulated a set of differential equations that corresponds to the data. So we did this with MMPs, TIMPs, ECM levels, and then we needed a cell type that actually produced these corresponding proteins. And so this is the minimum number of equations that we needed to actually be able to, that we could actually capture the data, so to speak. And so We used a global search algorithm to try to curve fit the data. So what you would actually do is you actually start with a local minimizer, or find a local minimum, and then I guess in short, what you do is you find a bunch of local minimum, and then you assume that the minimum of all the local minimum approximates the global minimum, so to speak. And so there's more details to it than that, but that's all I'm going to say at this time. And so this right here is the corresponding curve fits that we got here. And so we do a pretty good job of capturing it here, missing some of the details, but still do a pretty good job. We start to get the dip here, for example, with the good healers. Do an excellent job with the bad healers. Easier to capture, though, because there's less variation in the data. And so these are the corresponding curve-fitted parameter values. So like with the good healers, this is basically saying that, with the one patient subgroup, this high level here is basically saying that there's a high level of production of MMPs, whereas with the poor healers, we're actually getting a high level of production of the TIMPs. From there, we conducted what's called a sensitivity analysis. We actually did multiple sensitivity analyses, but basic idea, is, if we make a small change to a parameter value, how sensitive to the system at large, or how does that affect the system at large? And so with the classical sensitivity analysis, this is a local analysis that's actually dependent upon the actual parameter values. And so we're able to identify a number of parameters that are sensitive for the good healers, and slightly different set, but similar for the bad healers. And the reason that it's slightly different too is that it's dependent upon the actual parameter values that were actually curve fit. And
Classical, there's so many versions of sensitivity. Can you say a little bit more what you mean by classical?
yeah, for like formulating a like a Fisher information matrix. So basically, it's a matrix of partial derivatives. And looking at changes. So you have a matrix of partial derivatives, and then you evaluate them at the.
Yeah, but a lot of people, what are you choosing to differentiate?
Yes. The derivatives, partial derivatives of the states with respect to the parameters at specific time points. So.
Solve those with, we did ODs, that we solve those over time.
Yes. Yep. So. And then we also did a global sensitivity analysis, and what makes this global is that it's supposed to be independent of the parameter values, and so, but the one thing that you have to do is actually define a range of values for which to conduct the analysis. So you take a parameter and say what would be a large range, and so if it's large enough, then we're saying that this range for which we're conducting the sensitivity analysis is going to approximate a global response, so to speak, to make it independent of the parameter value. And so we did this using Latin hypercube sampling combined with a partial rank correlation coefficient analysis. From that, so I'm just going through this in brief, but from this we were able to identified 4 parameters that were actually sensitive, which is different than what we had for the classical or the local sensitivity analysis. So what we did from there was we actually tried to compare the two, try to do more of a comparison of the two. And so this is one of the things this is one of those things that I haven't seen done in the literature. But the way that we tried to compare the two would be to try to use the global analysis and try to use that to approximate a local analysis. And since if you're using Latin hypercube sampling, it's dependent upon the range that you select for each parameter value. And so what we did is we defined a narrow range or a narrow window for each parameter value around a given curve-fitted point. And so like if you take a parameter value and say, suppose that there's a 5% error. If we take that 5% error and then use that as our range of values for parameters, what happens then? And one of the things that we found is that by doing that, our approximation to the local analysis, ended up giving us, results that were overall similar to what we were seeing in the classical sensitivity analysis. And then the other thing that we did was we actually looked at what happens if you go from, like, say, that 5% window out to the largest range that we would consider.
PRCCs with this?
Yes.
Oh, okay.
Yeah, so it's LHS combined with PRCC.
Funny because the numbers over here, I mean, I thought the numbers had to be between, you're not giving us the LHS numbers.
No, I mean, I'm not getting into a lot of the details. Some of that's because of time. Yes, yes. Yes, yeah. So the classic way of defining sensitivity. Well, so you have the classic way of defining sensitivity is that you have a PRCC value that's greater than 0.5. That it can be between -1 and 1. It's greater than 0.5 in absolute value, and then on top of that, you have to have a p-value less than 0.05. Yeah. So. So in that regard, we actually formulated our own metric to try to get this down to, comparing, to make it easier to try to compare values. And so what we did was 1 minus the p-value times the PRCC value. I think we squared that and then multiplied that by the number of simulations that we did with that and took the square root of that. And so but our results for that were for the most part, were similar when we did that. So we came up with our own metric on this too. So that's why these numbers here are not between -1 and 1. So go.
So last time we had this discussion, we were talking about p-values in a mathematical model, and I'm still sort of confused.
So I mean what? Let's see here. What's the quick way of being able to say that?
Being that couldn't you always run more simulations and everything?
Right. Well, what's happening here is that there's random samplings of the parameter values, and then on top of that, random combinations of those different parameter values. And so then what you're doing is you're comparing your solutions for these different combinations at specific time points. And so there's.
So I mean, each parameter will have an effect unless they magically mathematically fall out of the. There's no stochasticity in this, right?
Well, what you will find because of the randomness of this, you will find low levels of sensitivity for all of the parameters with regard to each of the states. Yes, low levels of sensitivity. Yeah, we define that as being insensitive when you're below a certain level. So.
Sorry, is it a deterministic model or a stochastic?
The model itself is deterministic, but the random sampling creates creating this effect. So yeah. Let me finish this up, and we can always talk about that later. And so I've only got 1 or 2 slides left here. And so actually one of the things that was interesting about this, going from the window of like 5% out to 100%, we had one parameter in particular, K4, that ended up being locally sensitive but globally insensitive. But it's actually an important parameter in the model because it actually measures the interaction of MMPs and TIMPs. And so, a couple suggestions or a couple thoughts that we had on that is that this can actually show, number one, the importance of selecting an appropriate window or appropriate width for the parameter space in which you're going to conduct the analysis on, and then you could even perhaps try to use this to try to determine more of a physiological region in which the parameter is sensitive, because you could make an argument that parameters are sensitive in one region but not sensitive in another region. And so in conclusion on this particular project, we have good agreement with the good healers, excellent agreement with the bad healers. We've identified sets of sensitive parameters, and we try to explain differences in sensitivity values. We've recently obtained the individual patient data, so we want to start looking at that and try to start analyzing that, especially in the context of our model, and also look at predictability. And so a lot of times ways of thinking about predictability would be, if I curve fit half the model, can I obtain the other half of the model? And so this work was done by pretty much almost entirely by these two students here, with a little bit of a couple suggestions from Marissa Eisenberg, who's been here before. And then in general, Some other people I've worked with are some people at the Ohio State University Medical Center. I've also worked with Renee, and I'm working now with Suzanne on the optimal control. And then these are a bunch of students that have done most of the work that you've actually seen in this talk. And so this is kind of an overview of everything that I'm currently working on, so to speak. So, all right. Any? So other questions, or should we get? Yeah. Chris.
On that last part, you were talking about having a set of essentially with the good healers and the bad healers.
Yes.
Is there any characteristics that you could look at that would say that this group of people or this person would be likely to be a good healer versus a bad healer before you actually get into digging into their bodies?
Well, so I mean, there's a study that basically said that there was another study that actually said that if there's like 82% wound closure at the 4-week point, those wounds are much more likely to heal than if you're less than that. So what they did was that was the criteria that they used for, in this separate study to determine, to try to determine good healers and bad healers. So I guess they didn't predetermine that. They went back and looked at that retrospectively.
Yeah, I was just thinking that it might be useful
Right.
if you could tell if somebody was going to be a good healer up front. That might change how you treat them.
Yeah, I mean, one of the conclusions from their study was that the ratio of MMP1 to TIMP1, can be a predictor of a healing response, at least at the 0-week point and 2-week point. So those are some of the conclusions of their study. But I mean, actually, that's even one of the questions I want to get at. Would be to how well can we actually predict a healing response? Look at a question like how many data points would we would you need to try to see how if you can reasonably predict healing to a degree. Yeah, go ahead.
Do you see a fading of the technique's ability to be useful due to possible changes of flora of the bacteria that are growing in the wound as you apply repeated treatments of oxygen therapy?
I would expect that over a long enough period of time that could be an issue, but I guess over the shorter time scale, a few weeks, I'm not thinking about that as much, but I may be wrong in that. So anything else? Okay. Thank you very much. Thanks.